Hey guys, welcome back to Introduction to Computer Networks at NTU. This is week 14, episode 26, right? There's nothing else to remind you about except that Polly needs to cancel the office hour today. Okay, that's during the lunch hour because of a meeting, all right? Good, and let me say good morning to Boyu, Ethan, and Chenru. All right. Now, let's move on to the next topic. Yesterday, we learned about distance vector. It sounded interesting, isn't it? It's very much how human propagate information, right? And gradually you collect more information, more diverse information about something, and you get to comment better, or you get to route data better, okay, to a destination. And today, we'll start by exercising, okay, the algorithm we learned, so particularly the distance vector algorithm, and through an example, okay. And I have to say that for such a algorithm, which is very distributed, okay, each of the nodes just doesn't know exactly what is the best, okay. Yeah, you just don't know. So think again, right? We should all be humble. How do we know, right? How do we know we know? That is the question. So distance vector routers are also like us. They never really know they know the best. So they continuously loop and see that they hear more, and so that they can reach a better decision. Okay, so this is the characteristic of distance vector, and this example, okay, is gonna ask you to play God. Okay, so there are three routers. This is the easiest example, but even with the easiest example, you will see that it's actually hard, okay, to develop the distance vectors for each of the nodes in this small network. All right, so let's go ahead and start playing the first video. Because when each of the routers starts, there's a initialization phase, and we never talk about how a table initializes itself, right? How each router initializes the distance vector to begin with. Okay, so in this example, in a way that Polly would try to fill you in with the details. Okay, the algorithm sounds really easy, but from this example, you will see the full detail. All right, so this video, two parts. One is to initialize the distance vectors at t0, the initialization time. And then you will see that the nodes will begin to propagate this initial distance vector and then try to update its distance vector based on the distance vectors coming from the neighbors. All right, so there will be t1. And particularly, you will see one of the nodes developing T1. Okay, developing the distance vectors in T1. So I would say this video is quite important. Okay, 5.5 minutes. Let's see if you can follow through. Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. So the example this time, very simple, only three nodes, X, Y, Z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. Yeah. In node X, okay, the distance vector of X is initialized this way. For destination X, well, it's itself, therefore, distance 0, it does not cost anything, okay, to transfer data from X to X. To go from X to Y, let's initialize it to the link cost of XY if they are adjacent to each other. So, to here. XZ, so XZ. They're adjacent, therefore we use the link cost between x, z. Similarly, you do the same thing to initialize dy for node y, dz for node z. Now, hey, in node x, it maintains all neighbors' distance vector, all right, but at the initialization phase, node x did not receive anything from y nor from z yet, so dy and dz, these two vectors, are left null. Okay. So I'm just using the sign of infinity there, okay, to represent their norm. Similarly, for dx and dz in node y, and so on and so forth. So this is how you initialize, okay, the initial distance vector table.
which is composed of 3 vectors. Okay? You maintain your own vector, you maintain also the neighbor's vector. Now, once the vectors are initialized, each router will what? Notify the neighbors. So this vector here will be sent from x to all the neighbors, y and z. Similarly, node y is going to send its initial table to x and z. And similarly, z sent to y and x. All right. And that's why, in the next cycle, node x here in the table is going to see dy from node y, dz here from node z. All right. Now, with neighbors distance vector in place, now we can begin to calculate the dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Bellman-Ford equation says we try through all the neighbors of the source. X is right here, the source. 2 neighbors, y and z. So yeah, we do have 2 entries here. One is assuming neighbor being y. Second, using neighbor z. So for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now in this case, neighbor happens to be the destination, so this is 0, as dy y says 0. Link cost xy, 2. So 2 here. Now for the second neighbor, z, link cost of xz, 7. So 7 right here. Shortest distance from neighbor z to destination y. Then we need to look up the table. From z to y. Right here, it says 1. So 7 plus 1. This is 8. And this is 2 only. Therefore, y here wins. Y is the next hop router to y. So therefore, we write 2 right here for x, y. And now we derive dxz. So from x to z. Again, from the same source, 2 possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. The shortest distance from neighbor z to z, trivial. And it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. To go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Now x here acquired the new distance vector. It's going to what? Send it to all the neighbors. So this is the first cycle, calculating the dx from the x's point of view. Similarly, node y there is going to be calculating the dy. Node z there is going to be calculating the dz because it's receiving dx and dy.
All right. That's exercise, exactly what you saw in the video. All right. So this is the exact same network, you see. 3 nodes, x, y, z. We just developed dx at t1, right? But you see dy and dz. So node y and node z would update each of their dy or dz as well. So quiz 45 is asking you to develop dz in node z at t1, which is this. We just finished doing this, right? That is to develop dx at x, by updating this value and this value. And you see that, hey, 2 to remain the same, but we do need to make a change according to what information comes from y and z. Okay, so similarly, let's do something for z. So this time we calculate dz for no z. That is asking you to reassess dzx, and dzy. All right. So guys, for this quiz, I ask you to show the full derivation. Because this is a quiz, or this type of questions, it's better that you show the derivation so Polly can grade your solutions better. Sometimes you just have arithmetic errors, but if you just give the end results, and it happens to be wrong, then probably we need to deduct all points. So guys, show the full derivations. As long as I see that you know how it works, you get the full score, even though the final values you ended up having can be errors. Okay, so show the full derivation. Now let's go to the score space. And guys, the goal of this quiz is not so that you get things right. The goal of this exercise, of this quiz, is so that you exercise. Okay, so you guys are allowed 8 minutes time. So take your time, show the full derivation. All right, so let's start counting time. 8 minutes. see you guys did well. Yeah, a lot of times when I see this, that's actually okay. All right. Yeah, because I can tell that you guys get the idea. But showing the full derivation, that is always the safest thing to do. Yeah. But I probably can understand that during the exam, right? You do need every seconds of time you have. So, yeah, probably would actually consider, yeah, as long as you give enough detail that probably can tell. Yeah, you get the idea. All right, very good, guys. That's the whole point of the exercise. All right. And now let's move on. The second video is still about the example. What we did is to develop a table, the dx, right? What about dy? So in this next video, you will see probably deriving dz as well as, probably developing dz as dz at the no z, and then dy at no y. So this video a little bit long, almost 7 minutes. Okay.
Let's try to calculate the distance vector of z together. So you see, it will be the shortest distance from z to every possible destination in the network. And in the network, it's very small. Starting from z, there are only two possible destinations, x and y. So we just need to calculate dzx and dzy. Now let's calculate dzx first. According to Bellman-Ford equation, okay, so what we do is to try to find out, okay, through all these neighbors connected to the source, okay, which one leads us to the shortest path to the destination x. Now, in this network, we do have two neighbors, okay, connected to z. So let's try the first neighbor first, which is z. So we'll be using the link cost from the source to the neighbor. So link cost from source to neighbor, z to x being 7. And then based on what the neighbor knows, okay, the shortest distance to the destination. In this case, neighbor is x, destination is also x. Now we look up the table. So dx here being known to z, according to that, dx is 0. Now the second entry, the second neighbor is y. Okay, so we'll then take link cost from z to y, which is 1. And then based on y knows the best to the destination x. So dyx, okay, is the value we need to add link cost zy to. And according to the table, okay, dy says dyx being 2, therefore 1 plus 2. So going through x, we get a pass. The cost is 7. Going through y, we get a pass that the cost is only 3. Therefore, 3 wings. Okay, so you see here, to go from z to x, the shortest path distance is 3. And the next hop is obviously y. Well, let's calculate the other entry, which is zy. Let me clear the markup first. All right. Okay. Again, according to the Bellman-Ford equation, source is z, and the destination we wish to find out the shortest path cost is y. Yeah. In the Bellman-Ford, we'll try, right, for two different neighbors in this network of z and see which lead us to the shortest path. So let's try the first neighbor here, x, link cost being 7 again, and then, what about dxy? Now let's look up the table. It's dxy, therefore, yeah, the shortest distance is 2. So we ended up adding 7 to 2, which is 9. That doesn't look so good. What about the other neighbor of z? zy is 1 again. What about the shortest distance from y to y? And hey, it's itself. So y to y, the cost is 0. So okay, this other path going through y give us only path cost 1. Therefore, yeah, going through y, this gives us the shortest path from z to y. And therefore, we update the entire dv, which is now 310. We can actually continue and calculate what is dy, isn't it? So there are again two entries, yx and yz. Let's calculate yx first. Okay, this time y is the source and destination is x. Again, we need to try through all the neighbors of y. So let's start from x. Okay, so x in the middle. source being y, destination being x. So we go through link yx, which is 2 here, and then find out what is the shortest distance from neighbor x to the destination x. So neighbor and destination happen to be the same node. According to the table, x, yeah, the value is 0. So here, going through neighbor x, ooh, nice. Total cost is 2. The other neighbor, so y's other neighbor is what? Z. So z in the middle here. Link cost yz, 1. What about the shortest distance z knows to the destination x? So dzx, we'll have to look up the table here. dzx, which says 7. So the best path, okay, going through neighbor z is unfortunately, yeah, costing us 8. So comparing the two, yeah, the path going through neighbor x is better. Okay, so y, x, and then reaching x. So total cost 2. So we can now update, yeah, dyx to 2. The second entry in the distance vector of y is dyz. Okay, so again, starting from y, going to the final destination z. So starting from y, and this time final destination z. We'll have to try through both neighbors. First neighbor being x, link cost from y to neighbor x is 2. The shortest distance from x to the final destination z, oh, dxz. So let's see, dxz. Yeah, the entry in the table says 7. Second neighbor being z here, so yz, the link cost is 1. Nice. What about the shortest path from z to the final destination z? Yeah, it's actually quite straightforward, isn't it? zz, trivially 0. And 9 comparing to 1, which one is shorter? 1 here. At this point, we can also update the entry dyz. And this is how we come to the distance vector of y. So we now finish deriving all the distance vector tables at time t1. What you see also is this. Look at this. dy and dy, okay? Between t0 and t1, dy did not change. Therefore, dy here, no y here, does not need to propagate the data, okay? Propagate the vector to no x and no z. While, okay, when x here finds out the dx, which is different, okay, from t0's dx, we need to propagate dx to no y as well as no z to calculate the table for t2. Similarly here, z find out the new dz being different from the old dz, we need to propagate also. Okay, dz to no x and no y. Therefore, the two other nodes can calculate if the dx and dy needs to be changed further.
All right, so the last video then is let's develop all the distance vectors at T2.
So after the quiz, you'll see dx is changed and dz changed as well. So no x and no z will be propagating, okay, the newly discovered, the better distance vector, like this. Okay. So no x receiving the update is going to replace this with a new distance vector. Just like y here, okay, this vector here is going to be also replaced with a new vector from z. Similarly, this vector here is going to reach z, and z is going to update from 0 to 7 to 0 to 3. Now, what's a bit special is this, okay? In the quiz, you see that dy here at no y is actually not changed. Therefore, no y here is not going to distribute to 0, 1, okay, to x nor to z. Okay. So this stays the same. Therefore, this and this stays the same. But no y here is going to receive a new dx and new dz. Therefore, this gets changed to 0, 2, 3. This gets changed to 3, 1, 0. You see that in cycle number 2, x, y, and z, they actually converge. Okay? The view is consistent, and they all converge to the shortest path, okay? The least cost path. So in this very simple example, we see distance vector using the Bellman-4 equation works really well, converges in 2 cycles.
All right, so in that example, very simple, we actually developed the distance vectors from the initialization all the way to the system converging. But you see that for such a network that assumes all the link costs are static, yeah, that's quite straightforward to develop the distance vectors towards the end. But on the internet, these link costs or even the routers, how they connect to each other, may change. Okay, so the issue coming next is this. In this distance vector, so there's a very interesting characteristic called bad news travel slow, and relatively speaking, good news travel fast. Okay, so the first video on this topic is to show you first the easier case. When there's good news, it travel fast.
So one very interesting property with the distance vector routing is this. Whenever there's a good news in the network, it travels really fast. Okay, so when there's a better route, it gets propagated really fast and everyone converge really fast. But if it's bad news, meaning if a route suddenly go bad, okay, it will take a long time for everyone to discover, okay, the route is really bad and we should really be going another way. So let me describe the first case, the good news travel fast case. So recall. Okay, this is the change where the link between x and y is reduced from 4 to 1, so good news. The node is going to detect local link cost change and update the routing information and trigger Bellman forward. If the distance vector changes, then send to the neighbors. So here, link change from 4 to 1. So at time 0, y is going to detect the link cost change and update its DV and inform the neighbors here and here. So next point in time, z here, is going to receive this distance vector from y. Okay, it's going to see, oh, the shortest distance from y to x is now 1. Okay, therefore, z is going to update the shortest distance to what? 1 plus, the cost from going from y to x, which is 1 now, that is 2, which is better. Okay, so z is going to update its own dv and send it out to the neighbors. And y is going to receive z's update. Okay? Z says, okay, the shortest distance to x from me is 2. And y sees that, hey, I do have a direct connection. My shortest distance is already 1, right? Your shortest distance to x is 2, plus the link cost from y to z. This path is not better. Okay, so y there will not discover a new path, okay, a better path to x. Therefore, distance vectors stay the same. Okay, no more message being sent out. Okay, back to z. Network converges. Everyone goes to the steady state. The second case is the bad news travel slow. So you see from the scenario, the link cost instead of dropping to 1 now goes up to 60. Super bad news. Of course, x and y here would detect there is a link cost change. But in this scenario, it would take us 44 cycles until the network goes back to the steady state, until they all converge to valid shortest path. Okay. Now, bad news travel slow, meaning routes converging slowly. Okay, that is also referred to as the count to infinity problem. Now let's go to a quiz to see what's going on there. Okay.
All right, and this is the quiz. All right, so we'll go through this example and experience bad news travel slow. All right. So it's the same network you saw showing good news travel fast, but the link cost changes now from a shorter distance to a longer distance, which is the bad news. Okay, so what Polly would do is this to show you, okay, the table here, okay, and so that later on you guys, you will see that the result is this. Later on you would develop then, okay, y's table, so dy in particular, okay, so get these two values. All right, so to show this, Polly is going to play a video. This one is 2.5 minutes long, okay, not so long. Observe so that you can do dy, okay, with confidence.
Yeah, quiz 35, the scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from dx. Let me just show the final result real quick. Yeah, the xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through two neighbors of x of the source, that will be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through the first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from node y in order to find out, right? That is y's perspective. So that's in dy came from node y earlier. So dy y, then it's 0. And then, yeah, for the second neighbor, z, what is z's perspective, the shortest distance to y? That will be what? dz, to y. So dz to y. And that is in, distance vector of z came from node z earlier. Z to y, it says 1. So we put 1 here. Okay. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, no z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z.
All right, so now we're done. Developing x dx. Now try developing y's dy. All right, so let's go to the discourse space. Good. Similarly, show the full derivation. Okay, then Polly knows that you get it. And to ensure that you guys have a good amount of time to actually exercise instead of trying to get it done quickly, let's allocate some 10 minutes time. How about that? All right, 10 minutes. So guys, take the time to exercise. So guys, hey, what Polly came up with and what you guys have are very different. Oh, finally, Ray. Isn't it? Finally, Team 23, Ray. Yeah, so the way you do the calculation is the same as Polly's. It should need more iteration to update dzx and dxz. Exactly, Team 23, Ray. Because y is now calculating, and all y know is just, this dx and this dz that it has received from the previous cycle. At this point in time, t0, right after the change, y doesn't know this yet, right? Because, yeah, this is t0. And x begins to recalculate, y begins to recalculate. Similarly, z here will also begin to recalculate. At this point in time, y does not know, right? dxz should be 50. Hey, why does it know? It doesn't know yet. Guys, do you see that it's a little bit tricky? Yeah, so I guess you might. So many of you say 51, right? That is because you know what? Hey, you see, 4 is changed to 60, right? And you are trying to find out what is the best route. I mean, you're trying to update y's table, right? And y's distance vector depends on what is the cost this way, what is the cost this way. And now you're trying to fill in z's best route to x. And you see, this is obviously shorter than 60 plus 1. But you see, you're playing God. But z or x or y, each of these is just a router. A tiny, tiny, tiny little router. Okay, none of them is God. So z at this point is actually not sure, okay, that this has been changed to 60. So yeah, this is a little bit tricky. And therefore we want to take things slow. All right, guys, see if you can follow the next video, Polly developing dy. Okay, so pay attention this time.
dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is as a human, you see the global topology, you know it's 60. But distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cos is link cos yx is 60, link cos yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6, 6 wings. Okay, and that is actually going through no z. So y is going to pick, okay, saying to go to x. Let me send it to z first. And then z says, I know a way to x, which is, yeah, the old impression, right? This way. So you see the packet there is going to go y to z, z to y. But y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. Okay. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x.
All right, so guys, those who actually arrived at that 51 and 1, guys, you're smart. But the difference, the key here is, however, that the routers are not as smart as us. The routers follow the algorithm. So, okay, think again. The routers, the routing algorithms are based on all the information they have. They are not God. Okay, good. You know what? No worries. We'll exercise more. So there's 47 and 48. We'll do the distance vector routing in the bad news travel soul case for 2 more times and see if we get better. Okay, mimicking what the router would do. Good. Let's take a break. And guys, you can revisit your solution to quiz 47. Quiz 46. Okay, so if you didn't get it right the first time, revise it. Okay, and think again. You are human beings. You see the topology. You fill in the values that you should not, or a router wouldn't know. Okay, good. All right, so let's take a break for 10 minutes. It's now 11:10. We'll resume 11:20 and use the time to update your solution to quiz 46. right, guys. Time to come back to the lecture. Okay. Sorry. Times to come back to the lecture. So we're still in the bad news travel slow, the topic. Okay. And in quiz 46, you have experienced a little bit that the route calculation is actually not as smart as how human beings would do it. Okay. So that's exercise that router mode of computation a little bit more. And this time, pay attention. The routers can be too smart. The routers will need to follow the algorithm. Okay, whatever the algorithms tell and whatever the existing information in the routers they can apply. Right? So let's try it again. And this time on quiz 47, it's the same scenario. With the link between x, y is now changed to 60. And that's try to develop z's table, okay, at T1. All right, so that is, let's go to the PowerPoint mode. Okay. Sorry, yeah. So we have achieved building this and this in T0. That is the time instance right after the link cost change. Okay, and this is happening here. Okay, X and Y right next to the link that we discover a link cost change. Okay, Z here has no idea there's a link cost change. Z is over here. All right, so Z has no idea there's a change. So Z will not be doing anything, okay, at T0 here. Good. Now, what about T1, right? Because X and Y change the distance vector. So they have the obligation following the algorithm, passing the X here to Y and Z, isn't it? And similarly, after Y changing the dy, passing that to X and Z. All right, so quiz 47 is asking that we recalculate, okay, table of Z at T1. All right, good. I hope it's clear. So let's go to the score space. Okay, the problem is here. Okay, so that is essentially doing the dzx and dzy. And once again, that's allowed time, plenty of time, so you guys can think this through. So we have 8 minutes. All right, so let's start counting time. All right, I think you guys have got it. All right, but just to make sure, right? So let's go through the development of Z's table. Okay, so this is Polly's version of it.
You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, yeah, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for T1 and T2. Right? And at T1, Z here can try to calculate dz because it now receives the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains two entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-4 equation already. Okay. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, two possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these two entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 wings. And therefore, we update dz to 7, 1. Okay. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z. Yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5, and next hop is z. Okay, so you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finish calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again. provided the new DZ. Okay.
All right, and next quiz is then to try to develop a Y's table at T2. Let's go to the Discord. Go to the PowerPoint mode, the whiteboard mode. All right, so let's develop Y's table at T2. So this is what we have now after quiz 47. And 48 is asking you guys to develop dy here at T2. All right. So I guess I had a feeling that you guys will be able to complete this quickly. So how about 5 minutes? All right. Let's go to the Discord space and let's start counting time. All right, guys, great job. Okay, and now I trust that you know distance factor very well, especially when the bad news will need to travel, okay, the network. So this last video is to show pollys version of derivation, but Polly would also develop further and explain how this particular scenario is going to take 40 something iteration to converge, right? We just went through 2 iterations only, T1, T2, and it's going to take 40 something more iterations to finally converge and stabilize.
Let me bring up the result. dyx, this value here, is gonna be 8. Let's look through it again. Okay, from y to x, y to destination x. Through neighbor x, neighbor z. Link cost 60, link cost 1. Link cost 60, the zx, look up the table. Z's x, 7. 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here, actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only $7 to go to x. And this is going to go on, in fact, because y here is going to announce dy also, okay, to all the neighbors. And z is going to recalculate the dz. And guess what? And the next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cost to x. So until, okay, in dz, the value becomes 50, 1, 0. Okay, and how many iterations would that be? Yeah, came all the way from 7 to 50, that will be 43 iteration, okay? And including the initial iteration, that will be what? 44 iteration, okay? Until, okay, z discovered the true path. Next, then y will discover the true path. And then everyone converge to the shortest paths that are really true.
All right, so I don't know if you like the bad news travel so characteristic of distance factor. But what I can actually tell you more is that there's actually a fix to this issue. It's a special mechanism called Poisson reverse. Okay, and the first video here is to introduce the idea. It's about 2 minutes.
The problem here is, okay, right after link cost change, when y is trying to recompute, okay, the best route to x to z, okay, particularly to x. Bellman-Ford algorithm says y needs to try, right, calculating the total cost through neighbor x, neighbor z. Through neighbor x, best distance from x to x is 0, trivial, but the link cost is suddenly 60, okay, just to get from y to x. So together, total cost 60. Okay, not very good. But the other neighbor here, z, was still under the perception that the best route is this and the cost is 5. And y here says the link cost between y to z is only 1. Okay, so y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach x. Y does not know. Z is actually under the perception that this is the best route to go to x. So Z is going to send the packet back to y. And y is going to send it back to z. Z is going to send it back to y. So this packet here is going to loop for a while, okay, until y discover, okay, the real shortest path to x. So z here, okay, being still under the impression that the best route is the one before the link change, okay, needs to know about the link change. Poisson reverse is working this way. This is to help, okay, preventing bad news travel slow. In Poisson reverse, y and x, okay, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, okay, all your shortest path routes to the other node along the link needs to be changed to infinite. Okay, that way it prevents, okay, y selecting z, okay, as the shortest distance to x.
All right, so the idea is actually quite get to the point. it can sometimes a little bit hard to get sometimes. So let's go through an exercise that we use Poisson reverse to avoid the bad news travel slow problem and convert faster. Okay, so this video then with the full example, 5 minutes and 15 seconds.
Let's use the same example to illustrate how Poisson reverse works. So taking one step back before we have the link cost change. Now z here will discover a shortest path to x this way, z, y, x. So shortest distance from z to x is 5, and the next hop router is y. Now, link xy here, the cost changes from 4 to 16. X, Y, these two routers being connected to the link will be able to discover the link cost change, but Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, when we're calculating the shortest distance from Y to X, we ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to X, therefore we do 1 plus 5, and we ended up having 6 here, okay, a funny value for the shortest distance from Y to X, which we see from the network after link cost change, there's no way this is the right value. So to avoid, okay, having confusion such as this, we should stop, okay, Z from keep telling Y this is the shortest distance. So Z tells Y instead, okay, the distance to X is not 5, instead being infinite. Okay. And that is what you're seeing here. Distance from Z to X at Y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. Okay. If this node here discover there's a route coming from the neighbor and using itself as the next hop. Okay. So if Y here discover in one of the neighbor, okay, and this neighbor is using itself, okay, as the next hop to a destination, okay, set this entry here in Y's table to infinite. With now dzx being changed to infinite, the way we calculate dy in iteration t0 will be different. Okay, so dyx particularly is the entry with different value. It was previously 6. Okay, but now let's see how it's going to look like from y to x. Okay, there are two possible neighbors, x and z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor x to destination x, dxx. From second neighbor z to the destination x, dzx, dxx, dzx. Set up table, xx 0, zx infinite. So 0 here, infinite here. Comparing the two, yeah, 60 better. Okay, therefore, shortest distance from y to x is now, yeah, the direct link xy. And then the next point in time in T1, z here is going to receive the distance vector from x and y, and this time dyx is 60. That's going to change, yeah, the result of the dzx, this entry here. So let's see, dzx. From z to x through two neighbors, link cost being 50 and 1, 50 and 1. The xx and the yx, the xx, the yx. So xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wings. And you see here, from z to x, yeah, we're taking just this link, zx, as a direct path to destination x. Quite different, isn't it? So we update dz, and dz is going to go to the neighboring nodes. Okay, and so y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx. Okay, two neighboring nodes, 60 and 1 are the link cost. the XX 0, the ZX, ZX, entry value being 50. So 51 compared to 60, 51 wins. So to go from Y to X, now the shortest distance is, this path. And in fact, at this point in time, so let's update the distance vector for Y. At this point in time, the network converged to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
All right, so that was full mechanism of distance vector. And now let's summarize and compare the two routing mechanisms again.
Now with both routing algorithms introduced, let's compare the two algorithms. LS here stands for link state. DV is the distance vector. Let's compare the message complexity first. If you recall, in link state, each router there needs to generate this link state report, and it gets propagated, broadcasted throughout the network. So each of these link state reports is going to travel all the links. There are E of them, and there are N nodes. Each will be generating these link state reports. Therefore, overall cost N E. In the worst case, in case the network is very well connected, the E here is about the scale of N squared. So overall, the cost can go as high as N cube. So link state message complexity, not good at all. Distance vector, on the other hand, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. So in terms of message complexity, DV is slightly better. Now, the second metric, the speed of convergence, the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being N squared. There's some optimizations one can apply that takes you to N log N time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much in the scale of the diameter of the network. But that is actually in the ideal situation. What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, the packets will be looping from router to router. So in distance vector, the convergence time is a little bit hard to predict. It really depends on the situation. On the other hand, link state, very predictable. I would say in terms of predictability, link state wins over distance vector. But under normal situation, distance vector's convergence time, is indeed the diameter of the network. There's not many hops. Even for a large network, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Things like that. In link state routing, during the phase the router is malfunctioning, the neighboring nodes will be advertising the wrong link state reports. And each router will be calculating the shortest distance based on the wrong link state report. But once the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, if a router is malfunctioning and reporting, for example, a short link cost to a particular neighbor, the node can actually falsely reporting the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DV and then pass the incorrect information further. Yeah, each node's table is going to be used by the other. Each node's distance vector is going to be used by others. Yeah, this error is going to propagate out throughout the network, and it might take a long time, yeah, for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness, yeah, link state here is still winning by a head, by a neck.
All right, so that was distance vector and link state routing. And so far, these two routing mechanisms are actually theoretical. Okay, so what exactly is the routing mechanism used by the internet? Yeah, okay, interesting. So Polly was taking a poll, right? As you guys are listening to the summary, you see the pros and cons of both routing mechanisms, okay? And many of you stick to distance vector, but Yuzheng, yeah, says link state routing, okay? So that's probably because of hearing the robustness part, okay, of distance vector, because misconfiguration can also happen, right? And so you might have shortages, okay, in distance vectors in a way that's more frequent and longer. But in link state, it would actually recompute and reconverge faster. Okay, so Yuzheng, I admire you. You beg to differ. All right, so all right, very good to see you guys' opinion. So Polly is just taking a pose and make sure that there's actually a swing of opinions. Okay, as you guys know more and more. Okay, so I think if you guys recall, and Polly actually do the statistic. When Polly first introduced link state routing, and many of you guys says, "Hey, I like it. It's simple." So that was 5 to 11. 5 prefers link state, and 11 prefers distance vector. And in the middle, after Polly introducing distance vector, 0 to link state routing, or after Polly finished introducing link state routing, talking about the issues of link state routing. Now no one likes link state routing. And distance vector win all the votes, and there are 19 of you saying, hey, definitely distance vector. And I think at the time, one of you, I forgot exactly who, says that, hey, link state routing, right? In order to maintain the information of the entire network, it's just not possible. It's not going to run on the internet. You are perfectly right. And I guess that's why people overwhelmingly voting for distance vector. Okay, and this time we still have a strong favor over distance vector, but Yuzheng says link state maybe. On the internet, which is what we'll be talking about, the real routing mechanisms used on the internet. And guys, guess what? On the internet, we actually use both. And I guess it has something to do with that link state routing is still simple, right? And it's a lot easier to debug, and it's a lot easier to maintain. So what happened on the internet, in a nutshell, over the wide area network, okay, we have special routers, more powerful routers we call gateway routers, that runs the distance vector. Okay, and these special routers, gateway routers, for each subnet we have just one. For each domain we have just one. And those domains are called the autonomous systems. Essentially, NTU, okay, the network entirely is one autonomous system. Okay, for example, Academia Sinica, it's one autonomous system. For example, UIUC, it's one autonomous system. Okay, or one company, Amazon, is one autonomous system. So these domains that seems to be under one administration, we now call them an autonomous system. In each autonomous systems, we'll actually install these powerful routers we call the gateway routers. Among the gateway routers, in order to find each and every domain there are on the internet, we will need to run a routing protocol that is memory efficient. Now, therefore, we do something like distance vector at this level, higher level. But within each domain, inside an administration, in order for our admins to manage local routing efficiently, inside each of these domains, we actually run, guess what? Yuzhen, you're not wrong. Hey, Yuzhen, you will be fine running a domain, within a company, all right? So consider taking a job being the network engineers, in a company. So link state routing is actually preferred, to do the routing within a organization, which you can imagine, right, being not big. So within Amazon, I would guess that they will probably use an extended version of link state routing, which you will hear about in the next topic, intra-AS routing. Okay, good. So that should take us and transition us smoothly to the next chapter. So we're just done with chapter 5.2, and we are now moving to 5.3, which we talk about the real routing protocols running on the internet. Okay, so the first video, let's go back. Okay, Polly just introduced autonomous system, but let's go through the full introduction. All right, so the first video is to give you an overview of chapter 5.3 and 5.4, and then and then we'll introduce the notion of autonomous system entirely. And then, you will see why we want to break internet routing in this two level of hierarchy. All right. So if somebody asks you how the routing is done on the internet, you say hierarchical routing. On the higher level, because it spans a really, really wide area, the number of domains is huge. We make it memory efficient. But within a domain, which tends to be controllable in size, so we run this protocol that is that converge faster, easier to manage, and more robust. That is link state. All right, good. So the first video, the introduction one, as you can see, it's a little bit long. So this is to make sure that you are on the you have a good foundation. All right, so introduction of autonomous system.
Next, we'll be talking about two routing protocols that are actually running on the internet. First is called the OSPF, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, BGP, is then based on the other routing principle, the distance vector routing. Well, to be exact, BGP is not just distance vector routing. It's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, OSPF is the routing protocol that runs predominantly within a network, a local network. While BGP, this other one, very, very critical, very, very important, is running on all these backbone routers, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple, and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. So until now, the way we're introducing these routing algorithms is actually very idealized. Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. Even taking a distance vector routing algorithm, which is already more scalable than link state, if we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, there's going to be how many? These many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes, okay, for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like, close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not gonna work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch, okay, you don't wanna go there. Okay, so even if we use a more scalable routing algorithm, distance vector, okay, consider it working on the internet, not gonna scale. Okay, we cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also gonna swap the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 gigabyte of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay? So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers nearby belonging to another organization, another system. Now each of these systems can work independently. The network admin hired by the organizations could decide independently, autonomously, okay, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, okay, the system admin can decide maybe distance vector routing is better, okay, more scalable, better. So all routers here then will be running the distance vector routing. Okay. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, okay, 1 or 2 routers and make them the delegate routers. These delegate routers, okay, at the higher level will interconnect. Okay, so this system's delegate routers and this system's delegate routers, they might interconnect. Okay? And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all of these routers in the backbone is going to run one routing algorithm. Okay, so distance vector or link state. Okay. Well, to just tell you ahead of time, okay, for internet, the backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. Okay. So you see 2 levels of hierarchy. Yeah, there's backbone network, and then each delegate router there associated with it is a local area network. Okay, so internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems.
All right, so that was autonomous system, okay, and why we need to have 2 levels of routing. The next video is actually 4 minutes and 22 seconds, which will run over the time. And given that Polly needs to run to a meeting to catch some very important discussions today, so we'll end the lecture now, today. And we'll continue to talk about autonomous system. At the high level, we run this distance vector style routing, and we call that the inter-AS routing. It's the routing protocol running in between autonomous systems. At the lower level, within an AS, we run the link state style routing, and that is intra-AS routing. And there are routers within a domain that do the link state routing computation. But these routers, among these routers, some of them would also do the distance vector style routing. Okay, and as you hear from the overview, on the internet, in intra-AS level, we actually run this path, okay, vector routing, which is actually determining entire path instead of the next hop. Okay, so there are some reasons for that because sometimes who else in the middle of the path matters. Okay, so before in domain select a route to reach another domain, it might want to choose a route without crossing some other sensitive domains. Okay, so guys, so this is just to prepare you guys. These paths we choose can sometimes be policy based, not the shortest distance based. Just like the world, okay, the relationship from our country to other countries, from one region to other regions, can sometimes be mutually beneficial to each other in terms of maybe dollar sign, but it can sometimes also be depending on ideology. Okay, what do you believe? Okay, that's not saying more, and this is after all a technical course. So let me declare that this is the end of the lecture today, and let me say goodbye, and I see you next week to talk more about routing on the internet. Okay, bye. Okay, bye. Oh, and by the way, for quiz 46 to 47, those are not tricky quizzes. So even if you made a mistake answering it the first time, it's perfectly fine. Okay, but you guys, I hope that you learned something. The goal is not to avoid mistakes. The goal is still to learn something eventually for real. Okay, so making mistakes a lot of time is something necessary. And some of you, very few of you, okay, are able to make it right the first time. But you know what? Allow yourself to make mistakes. It's very important. You need to be able to allow yourself to make mistakes. Particularly towards the end of the semester in Taiwan, everyone is stressed out, and it's okay to be imperfect. Perfect or not, either way is beautiful. Bye.